Okay, here are some problems with classification of first order DEs. So for both of these examples, we're going to check each one of the things: linear, Bernoulli, homogeneous, separable, and exact. Keep in mind that a DE could potentially be more than one of these. In fact, the DE y prime equals 0 is every one of those. It's all of them. So you can be more than one at a time, or you might be none. Okay. So I've given this DE in both standard form and differential form. You should pause the video and make sure that you could get from here to here and that you believe these are the same DE. Okay, hopefully you've done that. So is this guy linear? Oh yeah, that's obvious. We've got a y prime to the first power and a y to the first power. Obviously linear. We're going to spend some time later with linear DEs. And for linear, we like to put them in this form. I don't think this has a name, or otherwise I'd be using it. But if we were to put this guy in this form, we get P of x is just x and Q is 0. You should check that yourself. Make sure you believe that. Okay, all linears are Bernoulli with n equals 0. Remember, this is our regular, I don't want to use the word standard form because this is what we call standard form. But this is the regular form we use for Bernoulli equations. Clearly, I can write that guy right there like this. P of x is still x, and y to the n has to have n equals 0, and q equals 0. Okay, homogeneous DEs. So I'm going to use standard form right here. Remember, standard form is y prime equals f of xy. And in order to be homogeneous, we replace all the x's and y's with tx and ty, respectively. So if I have a tx and a ty, that would be a t squared xy. That's not the original. T's didn't all disappear magically. It's not homogeneous. Okay, is it a separable DE? To be separable in differential form, everything in front of the dx needs to be a function of x. Everything in front of the dy needs to be a function of y. So in this form, the way it looks right here, it's not separable. But if we divide through by y, so we take this and divide everything by y to get rid of that extra y there, then I would have x dx minus 1 over y dy equals 0. That's a separable DE. All my x's are here, all my y's are here. It's easier, in my opinion, with separable DEs to think about them in standard form, though, to cross multiply and see if you can get all your y's to the left side and all the x's to the right side. So if we multiply the dx over, remember we can't really multiply dx. What we're really doing is writing this in differential form, but it's the same thing. We can pretend like we can multiply it. So bring the dx up, bring this y down to the other side. So 1 over y dy is x dx. That's a separable DE because I've got all the y's on the left side and all the x's on the right. Okay, is it an exact DE? In order to be exact, here's our m and here's our n. M is xy, n is -1. I take the partial of the first one with respect to the wrong variable. That's in front of dx, so I take his partial with respect to y. The -1 here is in front of dy, so I take his partial with respect to x. So partial of the first one with respect to x is, or with respect to y, is x. Partial of the second one is 0. The derivative of -1, I don't care what you're taking the partial with respect to, that's just 0. Those are not the same. That's not an exact DE. Okay, second one. Here we are in standard form. Here we are in differential form. Check yourself. Make sure you believe that these two are, in fact, the same differential equation written two different ways. Is it linear? No, that's clearly, you should be able to look at that and just see. I've got y squareds in there, not linear. Bernoulli. That one's a little harder. You can have y squareds, but you need to be able to write it in this form. It has to be able to look like this. And no matter what you do to this equation, you cannot make it look like this. It's just not possible. Homogeneous. To be homogeneous, replace all the x's with tx, all the y's with ty. So if we do that, I would get a t squared x squared, a t squared y squared. I could factor out the t squared, replace the y and the x with a tx and a ty, pull out that, or combine the two t's together into a t squared. Hey, the t squareds cancel. I get back to the original. That is a homogeneous first order differential equation. Is it separable? No. In order to be separable, this guy here needs to be just x's in front of the dx, and everything in front of the dy needs to be just y's. Sometimes they may not look separable, but you can make them by multiplying or dividing by some x's or y's. But there's no way that you can get this y squared away from that dx because these are added. If these were all multiplied, maybe you could fix it because then you could divide through by y squared, but these are added. So there's no way to get the dx and that y squared right there away from each other. So it's not separable. Is it exact? To be exact, the partial here with respect to y, 2y, remember partial x squared with respect to y would be 0. X is a constant as far as y is concerned. So in front of the dx, we take the partial with respect to y, we get 2y. In front of the dy, take the partial with respect to x, we get 2y. We get the same thing both places. That means this is an exact DE. Okay, you should go through, rewind this video if you need to, check all those details yourself.